So we're talking about the resting membrane potential of a neuron. A neuron is also known as a nerve cell, and it's the way that we communicate thoughts, and it's also the way that your mind can tell your hand to pick up a pencil or to move something around on your iPad through this neuron, which sends messages down that direction. Sending messages from one neuron to the next neuron is something called an action potential. And when that action potential occurs, it rolls like a wave, starting at the dendrites here to the cell body and then down the axon right here. And then the information gets sent out the bottom and it sends that information to the next neuron down here. So we're not really going to talk about action potentials, but the reason I bring it up is because the resting membrane potential is not a thing. It's not like, oh, there it is, there's a resting membrane potential, it's right there. No, it doesn't work like that. It's not a thing, it's a state that the neuron must find itself in. Once it achieves this state, then it can send an action potential and your nerves can communicate with each other. So the resting membrane potential is the way that a nerve is storing energy. It has it stored up to just the right amount so that it can be triggered and send an impulse. You can call it an electrical impulse or a wave down to the next neuron, sending information along. So to give you an idea of what that would look like, we're going to go down to this little chart. So not all neurons, but just let's say for this neuron, we're looking for the inside of that cell, of that neuron, to be charged to negative 70. So when it reaches that charge of negative 70, then you can say, okay, we've achieved a resting membrane potential. And now it has potential energy that can be used. To use that energy, what will happen is you'll get a nerve impulse to use the energy to create an action potential. You'll get an impulse, and since negative 70 is what we would call polarized, now the cell is polarized. We would depolarize it and achieve negative 50. So as it gets closer, like as the cell gets more positive, going that way during an action potential, when it reaches this negative 50, that's the sweet spot to achieve an action potential and send that message along. But while it's resting, we're going to just forget about that for now. We're going to just have a polarized neuron, and it's going to be about negative 70. Okay, so when it's negative 70, when you've achieved this, what it looks like at the dendrites and what it looks like at the cell body is it's negative inside along the edges of the neuron. So negative, 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 inside along the edges. Negative, negative. Okay, cell body, negative, negative, negative. All the way down the axon, negative, negative along the edges. Both sides. Okay, and then likewise on the outside along the edge of the cell membrane, it's positive, positive. And we're slight positive outside along the edges, slight positive inside along the edges. So the ions that are actually out here, which is a huge abundance of sodium. I'm going to say huge and draw huge so you can get an idea. The sodium out here is very uncomfortable because it wants to go through diffusion to a place where there's less sodium. Well, where is there less sodium? It's going to be inside in here. And inside in here, we have an abundance of potassium. And potassium is going to get uncomfortable too because it wants to go through diffusion where there's less potassium. It wants to come out. And so that's basically what's happening when you have your action potential. You get some flooding. So you got sodium flooding into the cell, and then you get potassium flooding out. And it moves like a wave in this direction as that flooding is occurring. And that's how you're sending a message. But to get to that state, we need the resting membrane potential. And we need some components to achieve this. So let's go down and take a look at what you need. So what you need to achieve this is our neuron blown up, is sodium, potassium pumps. Okay, so the reason you need these pumps, and when you hear pump, think work. It takes work to pump something, pump up a bicycle tire. It takes some energy. Whenever you need energy, you need ATP. Okay, so the reason you need these pumps is because there are sodium and not one unit, but sodium and potassium leak channels. So this is an example of the potassium leak channel. This is an example of the sodium leak channel. They're all over the cell, in the dendrites here, and in the body here, and in the axon here. And what they're trying to do by facilitated diffusion is whenever you have sodium out here, it's naturally, what it's trying to do is go down its concentration gradient through that channel. And then when you have your potassium inside, it's leaking out. We're going to say leaking out because these are leakage channels, through its leakage channel to, so there's more potassium here, it's going to where there's less potassium out here. There's more sodium here, it's going to where there's less sodium in here. That's what it's doing all the time. So because that's doing that all the time, I'm going to delete that for a moment. You need these sodium potassium pumps pumping all the time. So for one ATP, okay, it's working with this guy, this sodium potassium pump, you get 3 sodiums pumped out of the cell. And for that same cost of 1 ATP, you get 2 potassiums pumped into the cell. And now you're creating this gradient where you're going to have more potassium inside, and you're going to have even greater abundance of sodium outside. That's a good thing, because as this happens, you're getting to that point where you're achieving your resting membrane potential of about -70. And then you're going to get what needs to occur. You're going to get that negative charge just inside the edge of the cell, and you're going to get your positive charge just outside. And that would be great because it's going to achieve that position that it needs to be in, being ready and being in a state of readiness for that action potential to occur.